Hey, hi everyone. So, I assume we all are familiar or have had some use case or have interacted with production grade large language models like ChatGPT. And we all do understand, right, that how a particular large language model works, right? And the core idea is that for a given sequence of input tokens or input word, it kind of predicts the next token iteratively, right? So if I give it this particular sentence as a sequence of input tokens, then these are the next tokens that it kind of predicts iteratively. So what is happening under the hood is that it's actually a model that has been trained on a very vast amount of data to actually be able to make these predictions. And the underlying architecture behind this model is the transformer architecture. And transformer architecture was first, I think, mentioned in this paper. So this is a landmark paper, attention is all you need, that first proposed the transformer architecture. And after that, I think all the present day LLMs that you see kind of picked up on top of this and created their own uh, production grade, very large systems like ChatGPT and other LLMs. So, in today's video, what we will actually try to do is to unpack this architecture in a very simple and visual format. So, there will be twofold objectives that we will be trying to cover. So first will be like a step-by-step breakdown of transformer architecture as proposed in this paper, attention is all you need, using Google Sheets. So what we will do effectively is that this architecture that you see on the right hand side of your screen, right? Again, I think just to give a quick brief about the paper. So this paper initially, the architecture, the transformer architecture that has been proposed in this paper was not effectively done for actually predicting the next token in the sequence, but this was more proposed from a perspective of translation. So there is an encoder decoder model which kind of was proposed for effective translation based models. But again, I think the decoder stack that you see on the right hand side. So on the left hand side is the encoder stack, and on the right hand side is the decoder stack. So this decoder stack was what got picked up, and a lot of modern day production grade LLMs use this decoder stack and the transformer architecture in here as their core model architecture. So the first goal over here would be to kind of visually represent this architecture in a very detailed manner on Google Sheets. So each step that happens within the architecture, and what are embeddings, what is multi-head attention, right? And what are different heads, and how this architecture and actually flows out end to end is what we'll try to achieve through a visual representation. And in the latter part of the video, we will try to code up this architecture that we have just discussed onto Google Colab. So again, we will be scaling down the architecture, and obviously the real world production grade architectures generally are a lot heavier and lot denser, but we will deliberately scale it down, and then we will code it up to see if we can effectively train the architecture to do certain predictions. Okay, so that's what you can expect out of this video. And again, the reason that I'm using Google Sheets and coding it up on Google Colab is to ensure that this is more like a learning format based video, and at the end of the video you can take away the Google Colab notebook and try hands-on by training a transformer architecture of your own. So that being said, let's start off with the first part. And before actually going into breakdown of transformer architecture, Let me also quickly give you a understanding of the data set that we will be using for today's discussion and for the context of this video. Now, what I have done over here simply is that each word each integer starting from 1 up till 999 is what I have written down in words. So you can see 1, 2, 3, so on and so forth, right up till 999. And what we will actually try to do over here is that we will try to train a model that takes in a sequence of words and tries to predict the next word. So 179, 180, 81, 182, 100. So if this is the input sequence, then the next word that the model should predict is 80, and so on and so forth. Now, the reason that we are taking this data set, obviously this does not have any practical application as such, but this is more just from a educational perspective, from a learning perspective, and to ensure that whatever model or the transformer architecture that we will be training can be coded up on a simple Google Colab notebook by using, I think, already free to use GPUs that Google Colab provides. And another reason that we are using this data set goes back to the fact that the number of unique vocabulary, or sorry, the number of unique words in this particular data set is only 28. And how is that so? So 1 to 19, 20 to 90, 20, 30, so on and so forth to 90 and 100. Now, any particular integer between 1 to 999, when written down in words, can be written as a combination of these words, which we call tokens, right? So for example, 799, 799. So again, this data set and the number of tokens in this particular data set is relatively very small, and we are deliberately using this so that we can visually understand and unpack how a transformer architecture is actually built, and we can then eventually code it up to see how it works. Okay, so let's start off. So I'll be doing a bit of to and fro between the paper itself and the Google Sheet representation of the transformer architecture itself, so that we can understand what each component in the transformer architecture actually looks like in a visual format, in a more mathematical way to understand that. Now, again, so the first thing that we do is, like, for this entire data set, we figure out all the unique tokens, right, or the unique words that kind of build up this data set. So that is 28 for us, and this is what we call tokens. Now, to give a real world analogy of systems like ChatGPT, the tokens will actually be very high. So it can be every single word in the English dictionary, and it also depends on the tokenization scheme that different entities follow. But yes, that will not be 28. That will something be of the order like maybe 200k, 300k, depending on what is the tokenization scheme that they're following, and effectively how large is the data set that they're training. But for the sake of this discussion, we'll assume that our vocabulary has 28 tokens. Okay. Now each token is assigned a token ID. So for example, 1 is assigned an ID of 0, so on and so forth. Right. Now, now we want to understand what are input embeddings and positional encoding. So each token ID is now represented as an embedding of length 4. Okay, so you can see that token ID 0 is represented by this embedding, which is of length 4. Token ID 2 is represented by an embedding which is of length 4. Now, just to briefly understand what embeddings are. So these embeddings are again learnable parameters that are learned during the training when the model is trained. And you can understand that this is generally like a representation of each word or each token, and it is used to understand some meaning, some context behind how these tokens are interacting with other tokens in the sentence. And these numbers that you see over here, these are the weights that get updated during the training, so that each token can have some meaning to it, and that model usually understands during inference. Now, again, for the sake of this discussion, we have assumed that each token is represented by an embedding of length 4. But again, when we train practical large language models, the embedding size is generally way higher. It can be like 500, 12,000, or even more than that. Because I think over there, the requirement is to obviously understand more semantic meaning and relationships across words. So you need embeddings of higher dimensions. But a broad understanding over here is that each token is represented as an embedding, which will be learned during the model training. Now, so if we have 27 token IDs, and each token ID is represented by an embedding of length 4. So we get like a token embedding table or matrix of size V cross T, which is 28 cross 4. Now, if we take one sample input, so when we are training a model, we are effectively training it on a given sequence length or context window. So we say that we assume that the context window is 10 over here, which means that every time we will be passing 10 input tokens to the model and training it for the 11th output or the target that exists, right? So 10 is the context window for our understanding, or for the sake of, or for the context of this video. Now, so what we do, so for example, if we take the first sample input, which is 121, 122, 100. So if we take 10 tokens in a sequence, and the idea is to predict the next token, right, which will be 20 over here. So what we do is we effectively look up the embeddings that we have just created. So for example, for 1, we effectively look up the embeddings that exist for token ID 0, then for token ID 27, so on and so forth. So for one input sequence, we kind of load up all the token embeddings that exist for the corresponding token IDs. So this becomes my token embeddings, right? So this is equivalent to the input embeddings which a decoder only stack will have. Now, once the token embeddings are sorted, like once we already have them, the next phase is to effectively provide positional encoding. Now, this paper, the architecture that is proposed in this paper kind of has a fixed positional encoding model, but generally present day LLMs and GPTs that are trained follow different positional encoding or positional embedding schemes, and some of them are probably fixed and some of them are learned during the training phase itself. For the sake of this video, we will assume that positional embeddings are also something that will be learned along the model training phase itself. Now, the idea behind positional embedding is to give a positional meaning for each word. So the very first thing, token embeddings kind of represents each token, and position embedding is representative of each position. So the word 1 is coming at the first position over here in this sequence length of 10. It is coming at the first position. So we provide a position embedding of dimension 4, and for the second position, so on and so forth. Again, the idea over here is that we are passing model some information around the position at which that particular token is coming in that particular input sequence. So token plus position embedding is what becomes my input to the model. Okay, so if you see, this is simply element wise addition of token embeddings and position embedding. So each sequence length of, so we have assumed a sequence length of 10, so there are 10 tokens over here. So for each token there is a token embedding, and then there is a positional embedding, and the input embedding is a summation of positional encoding and the token embedding. So this becomes my input to the model, and the dimension of this input will be L cross D. So L is the sequence length or the context window that we have over here, 10, and D is the dimension of the embedding, okay, which is 4 over here. Now the next part, and I think the most important part of a transformer architecture, is masked multi-head attention. So let's unpack and understand what actually is happening here. Okay, so for this video, we will be assuming that the number of heads that exist within this particular architecture is 2. Now, before we actually go into the workings for each head, the broader idea over here is that we are trying to establish relationships between each word to the other word in this sequence. For example, 1, how is it interacting with other words in this sequence, with 100, with 20, with 1, then with 100. So how is the interactions happening? So that is the broader, I think I would say, the crux behind what this attention layer effectively does. So we'll quickly go through how this entire self-attention layer is stacked. So first of all, as I told that we are going to divide it into 2 heads. Now each head will kind of learn some understanding or some relationship between the words. The second head will also understand some relationship and some understanding between the words, and then finally we will concatenate these heads. So let's take one head for example. So if we for example take head 1, then we initialize 3 different weight matrix, which is WQ1, WQ2, WK1 and WV1, QKV, right? Query, key and value matrices. Now the dimensions for WQ1 will be D cross DK. D is effectively what we have already learned, the length of the embedding vector, which is 4, and DK is basically D by H, which means the length of the embedding vector divided by the number of heads that you're actually going to have in this architecture. So for us that is 2, so DK will be 4 by 2, which is 2. So WQ1, WK1 and WV1, these are the weight matrices that are defined, and each of them will have a dimension of 4 by 2. Now the first thing that we do is to calculate Q1, right? And Q1 is nothing but matrix multiplication of input embeddings with WQ1, okay? And similarly K1 is input embeddings and WK1, so matrix multiplication over that. So again I have written the formula all across the Google Sheets, so I will also be passing you the access for this Google Sheet so that you can go through all the calculations and all the matrix multiplication, how it is happening all along the way. Now once we have Q1, K1 and V1, okay, which is effectively a matrix multiplication of the input embeddings and each of the weight matrices that we have defined. Now again, the reason I have kind of color coded these weight matrices is because these are learnable parameters that will be trained and updated during the training process. So the ones that are in color coded formats are the parameters that will get trained. So once we have Q1, K1 and V1, right? So each of them is like a matrix of dimension 10 cross 2. Why? Because we have 10 cross 4 matrix multiplied by 4 cross 2 matrix. So that eventually gives us a 10 cross 2 matrix. Now, the next thing that happens within each head is a scaled dot product, right? And what do we mean over here is that the matrix Q1 is multiplied by transpose of K1. So Q1 multiplied by transposed K1 and divided by square root of dk, which is effectively my dimension for the weights that we are defining, the weight matrix that we are defining. And this is just to normalize the scores. So when we do Q K transposed, so what effectively we are doing is Q1 matrix multiplication of Q1 and K1 transposed. Okay, so that's what we are doing. And then we simply divide it by square root of dk, which is effectively my dimension for the weight matrix. Now, this is where we kind of establish the fact that each word is interacting with other words, right? So this QK transport kind of covers the semantic meaning that each word, how it behaves with other words. So when a model is trained and when these weights are optimized, the model will actually understand how different words in a sequence interacts with each other, and the weights will be trained accordingly. So that is the core crux behind doing this scale dot product. Okay, and once we have this QK transport, now we add a casual mask. Now the reason that we do a casual masking over here is to ensure that words in a given sequence are not taking or considering the fact that how the interaction is happening with a future word. So for example, one will not take into consideration how it engages or interacts with words that come future in the sequence, but probably 100 will take into sequence all the words that comes prior to it and will ignore all the words that comes after to it. Now to enable this behavior mathematically, we implement a casual mask. So what is casual mask? So first we define a matrix which is 10 by 10. Okay, and why 10 by 10? Because the QK transport matrix that came as an output of Q1 K1 cross matrix multiplication in the last step is also a 10 by 10 matrix. Now this 10 by 10 matrix, we have to apply a casual mask. So how do we do that? So first we initialize a matrix in which the lower triangle is effectively having all the positions marked as 0, and the remaining positions are a very large negative value. Okay, so this can be a very large negative value. Then what we do is we just sum up the output from the last layer and we add a casual mask on top of it. Okay, so this is my scored masked matrix, a 10 by 10 matrix, which is this plus the last output. Now what we will do is we will do a row wise softmax. Okay, So what row-wise softmax does is, so in fact what softmax as a function does is that it converts a list of raw scores into probabilities that sum to 1. And how do we mathematically achieve this is so exponent of the individual raw score divided by summation of exponent of each of the other scores in that particular list. So we then do row-wise softmax across all the rows. So if you see, the sum of probabilities across each row will be 1. Now what casual masks helps is that it kind of, because this is a very large negative number, it skews down the probabilities for this to 0. Okay, and it only takes into consideration the lower triangle of this particular matrix. And this is again to consider the fact that we want tokens to interact with only, or probably develop understanding and relationship behavior of tokens that come prior to that. So that's the primary reason of doing a casual mask. Okay, so after doing a row-wise softmax on top of the casual mask that we did, this is the output that we have. And finally what we do is we do a matrix multiplication of V1 with the row-wise softmax output that we had. So this is like a 10 by 2 matrix multiplied by a 10 cross 10 matrix. So the output is a 10 by 2 matrix. So this is what we get as output of head 1. So after doing all this iteration, like after initializing, then Q1, QK transposed, then casual mask, then softmax, finally after multiplying it with V1, we get this as output of head 1. Now same thing is repeated for head 2 also. So for head 2 also we initialize the weights in similar fashion as we did for head 1. And then we repeat the same thing, which is QK transpose, then casual mask, and then finally multiplication with V2 and the output head 2. Okay. So once we have head 1 and head 2, we kind of have the final output for this multi-head attention layer. So what is this? This is nothing but concatenation of both the outputs across both the heads. So this matrix concatenated with this matrix is what we get over here. And this again becomes a matrix of dimensions 10 cross 4. Okay. So this entire thing in a nutshell explains what happens inside masked multi-head attention. Okay. Now after masked multi-head attention, the next layer is residual connection plus LayerNorm. So what is residual connection? So you see that there is an arrow that comes out of over here and is directly added to the add and normalize layer, right? So this is what we mean by residual connection. That is, for every next step, we are also considering or taking into account the residual connection with a step prior to that. So let me just explain this, what exactly we will be doing over here. So what the residual connection or how it will look like. Okay. So the output from the last layer, which is the multi-head attention layer, that is summed up with the input from a layer previous to that. So this is the residual connection that we are making. Okay. And this we do for all the elements. And that's how we get a residually connected matrix of dimension L cross D, which is 10 cross 4. Now, on this particular matrix, we will do a layer normalization. Now, layer normalization is simply done to normalize the numbers so that when we are effectively doing back propagation and the gradients are getting optimized, so it helps on that. So how it is done? Very simple. We effectively subtract the mean across all the elements. So we take the mean across all the rows, and then we subtract the mean divided by variance, and then we add a scaling factor. Sorry, we include a scaling factor gamma and also add a bias b, right? So let's assume that this is the gamma and beta that we will be using for doing this layer normalization. So how we will effectively do it is, I think we have done it using formula. So similar to what I've explained, that each element minus average, which is like mean of that particular row, divided by variance plus a very small number to ensure that to take care if the variance goes down to 0, and then obviously the scaling factor gamma and the bias beta. So this we do across the entire matrix, and the resultant matrix is effectively matrix that has been normalized, and this entire process concludes my next step, which is the addition, the residual addition and normalization. Okay. So once we have done this, now we will move to the next layer. So the next layer is position wise feed forward network, and the idea behind this particular layer is to equip the model to learn the non-linearities while training. So the previous layer, which was the self-attention layer, that was more about how the tokens are communicating with each other, and in this layer I think we effectively don't make the tokens interact with each other, but broadly the tokens learn certain characteristics of its own. So taking very simple example, like whether a token is a verb or a noun, and how does different non-linearities impact the predictions itself. So to learn that kind of behavior is why we have a feed forward network. So for computing or for showing the computations for feed forward network, we have defined two matrices, W1, which is like 4 cross 8 matrix. So these are weights again that will be learned during the training, and W2, which is an 8 by 4 matrix. So what effectively we are trying to do over here is that we are trying to first expand the output of the last layer into a larger matrix, and then we are condensing it. So this expansion and condensation will help the model to actually learn some non-linearities during the training journey. So the first computation that happens is matrix multiplication of the output from the last layer with W1 that we have defined, and the resultant output is a 10 by 8 matrix, and then we do ReLU on top of that. So ReLU is nothing but taking max of 0 comma each element, and this again is done to avoid vanishing gradient problems during the training journey. So ReLU activation is applied across this entire 10 by 8 matrix, and finally this output matrix is multiplied with W2 and condensed back to its original shape of 10 by 4. So this is what effectively happens in a position wise feed forward network. Now after feed forward network, we do another residual connection and layer normalization. So what is the residual connection that we are going to do over here? So output of the last layer, which is feed forward network, plus output of the layer prior to that. So that is the residual connection that we are establishing, and we are doing a layer normalization similar to what we did in this particular layer. So similar to that, we will be doing a layer normalization, which is again nothing but each element minus the average across that row divided by variance, and then scaling factor gamma and bias beta applied to it. So this we will do across all the element in the matrix, and the resultant matrix is effectively an outcome of feed forward residual connection plus layer normalization. So this entire thing that you see color coded as somewhat orange, so this entire thing, right from head up until feed forward network and residual connection and final layer normalization, is something that is called one transformer layer. So this entire thing is what we have just represented over here, with only one multi-head attention and one feed forward layer, and one add and norm after multi-head attention, and one residual and layer normalization layer after feed forward. Now in actual large scale production grade models, there are multiple such layers created. So attention plus feed forward, then attention plus feed forward. So there are multiple such layers created, so that when a model is trained, it kind of understand how different tokens are communicating with each other, and also develops some understanding of each token on its own. So that's the essence behind this multi-head attention and feed forward layer. Okay, and obviously a normalization after attention and a residual connection and normalization after feed forward network. So this entire thing is what we have covered till now. Now moving to the final layer, right? Like finally we want to effectively train the model, right? And we want to convert it into a format so that trainings can be done and back propagation can happen, and models can learn and optimize all the weights all along. So for the final layer, so which is basically this linear and softmax, right? So what we will do is we will initiate a weight matrix which is of dimension d cross v. So d over here is the length of each embedding that we defined, each token embedding, which is 4, and v is the vocabulary, right? So v is 28 for us. So a 4 cross 28 matrix is what we will define, and the final logits that are calculated is matrix multiplication of output from last layer with the W out matrix that we just defined. So this gives me a matrix of dimension 10 cross 28. Now we will apply a softmax across this final logits matrix. And again, softmax is nothing but smoothing out the distribution or representing these logits under like a probability distribution such that each row sums up to 1. Okay, so same as the softmax that we did in the attention layer. So similarly, e to the power each element divided by sum of e to the power across all the elements. So that is how we do the final row wise softmax to get the predicted probabilities for each token at that position. Now, how does the training happens? So let's say the input tokens that we considered for this example. So I've just written it over here. This is the same input tokens that we have taken into the consideration. So for each input token, we want to predict the target tokens. So what effectively we are doing here is, like, say the first input token is 100, is 1, then the target token for that will be the subsequent token, right, which is 100. And if the input token is 1 and 100, then the target will be 20. And if it is 120, then the target will be 1. So basically it is shifted right by 1 to get the target token IDs. Now, if the target token ID is 27, so taking the very first example, this means that ideally, if my model was working perfectly, the 27th token should have given a probability of 1 and all others should have been 0. Okay, so that's what we are trying to do over here, is we find out the index of 27th token and the corresponding probability that is represented here. Okay, and this probability ideally should have been 1 for the loss to be 0. Okay, so now how the model is trained is that it kind of gets the predicted probability for that particular token, which is the target token, and because it is not 1, it kind of now back propagates and optimizes the weight all across the network to basically understand that, okay, if this is the input, then this should be the output. So on and so forth, it does across all the input token IDs and target token IDs. That's how any particular transformer architecture is trained. And once the training happens across a lot of samples, so this is just one sample, but say that we have done this across n number of samples, the weights will get optimized in a way that now for any given input sequence, you can effectively predict the output token, which means that the probability for the predicted token will improve with time and you will be getting the right results. So that's how the prediction happens, right? That we are effectively taking for a given sequence. For example, if this is the input sequence and we want to know the next word, then the model will effectively give the highest probability score to that particular token ID, which it thinks fits perfectly after this particular sequence of input tokens. So that's how models are trained end to end. So now we have covered the basic understanding of architecture. What I would suggest is that you can go through this Google Sheet once. It will give you a clarity on how this architecture actually works. You can try it on by actually developing a copy of it and probably increasing the embedding size or taking any other vocabulary format and try and create this on your own, or just go through it. Everything is having a formula across the entire sheet so that you can see that which matrix is getting multiplied by which and how are the results flowing over and how is the final training and inference happening. Now, that being said, I think this wraps up the first part, which is step-by-step breakdown of transformer architecture. Now, what we're going to do is code and train a simple architecture on a small data set using Google Colab. So this is the Google Colab notebook that we will be using for coding up the architecture that we have just discussed. So a quick heads up. So you have to ensure that the runtime type is Python and you have selected T4 GPU when you are actually trying out or to execute this Colab notebook. And we will be using PyTorch libraries for coding up this entire architecture. Hyperparameters. So again, hyperparameters, we will try to keep them in sync with what we have just discussed. So block size effectively means the sequence length. So we have taken a sequence length of 10. So we will be initializing the block size to be 10. Max iterations, eval intervals, learning rate, eval iter. So these are all hyperparameters that are used during training and inferences. So basically max iteration means that how many iterations you will be doing for training that model, that how many samples you are going to actually pass on, so on and so forth. And eval interval is basically that at what intervals you want to evaluate the loss. So all of this I think will start making more sense once we go deeper into the code. And a few other parameters that I want to talk about, end embeddings, which is effectively the embedding size. So on the Google Sheets we took or assumed that each embedding has a length of 4. So that is what we will be keeping it. Number of heads. So again, number of heads that we assumed over here were 2. So we will keep it the same. Number of layers 1, because we had only one layer of attention plus feed forward. So we will keep it 1 as of now, but in practical models, right, we need to increase the number of layers. And dropout is something that controls overfitting of the model, which effectively means that some percentage of the neurons will be ignored during the training. So these are the hyperparameters. Now let's quickly create this data set, which is 1 to 999, all the integers written down in words. Okay. So very simple code for that. We define the ones, tens, and then first we effectively add 1 to 19, then all the 20s, right? 20, 21, right up till 99 is what is getting looped in over here. And then all the hundreds and followed by tens, right? So basically 100, 21, 122, so on and so forth, right up till 999. So this is where we create our very simple data set. Okay. So I've printed some samples in between, but this actually is like a longer data set, which effectively is something similar to what we have already discussed. So once we have done this, we see the unique words. So I call a set constructor on top of the words variable that we have just created. And you can see that these are the unique words that effectively constitute that particular data set. So we will be defining that as vocab. So this effectively becomes our vocabulary. And then we are also defining string to integer and integer to string dictionaries. This is just to effectively allow us to convert each word to the corresponding token ID and token IDs to the corresponding words. Okay. And then we just check the vocab size, which is 28, and this effectively matches with the vocab size that we have taken into discussions on the Google Sheets. Again, I think because this is a fairly small data set, so I'm just duplicating it so that we have a good enough data set for training as well as for validation. Okay, so let me just quickly do this. And the total length that it turns out to be is somewhere close to 35 lakhs roughly. Then we define two lambda functions, encode and decode. So what each of this will do is that encode, so for every given string, it will output a list of integers, right? So for example, let me just also show you. So if I encode 1 and 100, so it will give me the corresponding token IDs, and the decoder does the vice versa. So If I decode 17.1, it gives me the corresponding words. Okay, great. Now what we will do is we will encode all the words as a torch. Will effectively use the torch library, and we will encode all these words in a big tensor. Okay, which effectively means that all the words that we have generated, okay, they are then effectively converted into their token ID representation, and they are all encoded in a very large tensor. Okay, and first 90% is what we will be using for training, and the last 10% is what we will be using for validation. Okay, now I define a get batch function, which what it effectively does is it creates trainable X and Y, which means basically my input and target token sets for me, right? So what it effectively does is that for the given token length that I have defined, which is the block size, which is the sequence length that I have defined, it takes that into consideration, and it builds multiple, or it builds copies of, it randomly selects different sequence of input tokens and shifts it by one, and a sequence of output tokens. So I think if I just show you with an example, it will make sense. So this is what I get, right? So as I already told you, right, that we have defined batch size of it. So in case I missed explaining batch size, so this is nothing but what we are trying to do is that we are trying to process multiple independent sequences in parallel. So instead of just taking one input sequence X and one target sequence Y, we will be doing 8 such input sequences and 8 such output sequences, and we will try to parallelize the training process so that it happens faster. Okay, so this you can consider a third dimension on top of the other dimensions or everything that we have discussed till now in this Google Sheet. So effectively multiple copies happening together. So taking that into consideration, it generates 8 copies of so this is like 1 copy, 2 of second copy of input. So again, these are random sequences which are plucked out from the entire data set that I have, right, and corresponding target sequences. Okay, so these are the token IDs. So probably this doesn't make much sense as of now, so let me just decode it. Okay, so what I'm doing is the output that we have received over here, we are decoding it to understand that how are the inputs and outputs happening. So the first input is let's say 48, 849, 848. Then the output sequence or the target sequence will be this, right? How it works is that for 40, if the input is only 40, the output is 8. If the input is 48, the output is 8. If the input is 48, 8, then it is 100. And let's take like a bigger example. If it is 48, 849, then the, or probably 48, 849, 8, then the next output will be 100. So this is how this is simply working, and I create 8 sets of input sequences and 8 set of target sequences, so that we can run the training in parallel across 8 batches. Okay, just to exemplify what I have just explained, so let's take any random input and output combination and try to see. So when input is 6, target is 100. When input is 6 and 100, then target is 40. and so on and so forth. So this is the kind of training that we will do, or that's how we will structure our architecture, so that this is the pattern that the model learns. Okay, now let's start building and training the model itself. So the very first thing that we will do is to initialize the parameters, right, or the weights that will be learned during each training iteration. Okay, so again we will be moving a little bit to and fro between Google Sheet and Colab notebook, so that we kind of have a good enough understanding of which particular line of code corresponds to which particular weight matrix that we have just discussed. So initially, I think we are defining a token embedding table and a position embedding table. So these two things, and again, as you can see, the token embedding table has a size of v cross n embedding. So this is the same thing as this, which is 28 cross 4. So so we have defined a weight matrix of 28 cross 4. Position embedding, block size into 4, which means block size is effectively the length into 4. Okay. Then for each transformer block, we have to define two things, right? First is basically the heads, right? So again, if you see that I loop in through to number of layers, because as I told you that in practical scenarios, generally multiple layers of attention plus feed forward is enabled. So, and within each layer, then we have a nested loop which factors in the number of heads. Okay, so for our case, there is only one layer and two heads. So we will be defining the weights for each head. Okay, and again, three different weight matrices as we discussed. So if you remember, WQ, WK and WV, which is query, key and value. So we are defining key, query and value for each head for each layer iteratively. Okay, and the dimension for each is number of embeddings cross number of embeddings divided by number of head, which effectively means 4 into 2. That is what we are defining. Okay, then we are defining two layer normalization matrices, which will be used for the layer normalizations that we did. Okay, so layer normalizations that we did over here. So again, we are defining multiple ones over here. Okay, and then we are defining the weight matrices for feed forward network. Okay, so feed forward network, this is the one what we are representing. So idea is that we have to first expand it and then condense it back. So initially, if you remember, it was 4 cross 8 and then 8 cross 4. So let's just keep it same as what it was. So n embeddings is 4. So 4 cross 8 and then 8 cross 4. So these are the weights for these two weight matrices that we are going to define. And then there is a final layer normalization that we will be doing. I think that is something that we have not done over here, but you can assume that there is also a final layer normalization that happens after all the matrices or after all the feed forward and attention layers are covered. And then this final LM head is effectively this particular matrix, the last layer, right, which is D cross V. So 4 cross 28. So n embeddings, which is 4, and vocab size is 28. So these are the parameters that we have initialized. Okay. Okay, let's initialize these parameters. Let's call this function, and then we are effectively defining a lower triangle. This is again to take care of the casual masking. So casual masking, I hope you remember, comes from this part of the architecture, which is done within each head individually. Okay. Now let's code up each of the different layers. Okay. So first thing is the attention layer that we will be coding up. Okay. So attention layer, I think the input is coming from the last layer. So this input to the model, okay, this 10/4 matrix is what goes as input to the attention layer. So this X effectively represents this particular matrix that goes as input to the attention layer, and BTC essentially means that we are extracting the dimensions of this particular matrix. So why this is 3-dimension? Because as I told you, the third dimension, which is batch, is effectively taken into consideration to batch multiple samples, right? So this is T cross C, and batch is like a third dimension to basically equip the model to be computed or operate parallelly to each other. Okay. Then effectively we will calculate the head outputs. So we are doing the K, Q, V matrix calculation similar to this one, Q, K, and V. So this matrix multiplication that we just discussed is what we do over here, which is weights multiplied by X, which is the input, then again the weights multiplied by X, and so on and so forth. Then the next step is Q and K transposed matrix multiplication. So we will take a transpose of K matrix. Okay. So this particular operation is what is being done at this line. Okay. Then the next step is casual masking. So what we are effectively doing is that we have initialized a triangular matrix, right, with all the lower triangles as 1. So all the others which are 0 is replaced by a large negative value, similar to what we did over here. Okay. And then we basically, so this entire casual masking that we did, right, is something that we replicate using code over here, and then we do a softmax. Softmax again is nothing but converting the logits into corresponding probabilities, which is e to the power each element divided by sum product, as we have already discussed. So then we do a softmax, and then we do dropout. Again, as I told you, dropout is something that we do just to ensure that we are not overfitting. So some of the neurons are deliberately ignored in the training, right? And then this final output is this step. So this final output is this particular step wherein you are doing a matrix multiplication of row wise softmax with V1. Okay. And once we do it, you see that we have a for loop over here, which kind of iterates through all the heads. So first we do it for one head, then we do it for second head, and the final outputs are appended or concatenated over here. Okay. So this is the final output which concatenates across all the heads. So this concatenation that we did is what is represented over here. Okay. Then again another dropout, same reason, to avoid overfitting. Now this is the attention layer. Now coming to the feed forward layer, right? So feed forward layer, again for feed forward layer, the input is again 10 cross 4 matrix. So what we do over here is, like, first thing that we do is matrix multiplication of W1, which is my first weight matrix in feedforward layer, with the input from the last step. Okay, that we do, followed by a ReLU, that again that we did over here. Okay, so this is the second step, and third step is condensing back the elongated matrix to its original form factor. Okay, so which is this particular operation, sorry, this one. Yeah, so this multiplied by the second weight matrix. Okay, and then again drop out to avoid overfitting. Now both these attention layer and feed forward layer is basically defined or called in another function, within another function called transformer block, which takes care of the residual connection and layer normalization. Okay, so ln1, ln2, ln1 is for the layer normalization that happened after attention. Okay, so this layer normalization that we did after attention and the residual connection that happened. Okay, so x plus attention, then followed by the layer normalization. So this line of code in a way takes care of residual connection as well as the layer normalization layer. Okay, and the same thing happens for feed forward. So feed forward also, if you remember, takes into a residual connection and follows a layer normalization. So this entire thing, so this function transformer block covers this entire thing that is marked in orange over here. So all the workings that we saw in orange is covered in this part of code, right? Because this then iteratively calls the feed forward and the attention functions and does the residual connection and also the layer normalization. Okay, now finally we have to stitch it all together. Okay, so this function GPT forward, this effectively takes the input token sequence. Okay, and then it first initializes token embeddings. Okay, so which basically means that it figures out, so it's equivalent to doing a lookup. Okay, so this lookup that we did, right, for each token ID, it looked up the corresponding embeddings. So this is what this function is doing. Then position embedding is similar to the position embedding that we defined over here. And then there is a summation of token embedding plus position embedding. Okay, so this x plus p is what becomes my input to the model. Okay, and then after that we call the transformer block, which we have just defined. And again, as I told you, that this entire transformer block is done iteratively across multiple layers. So as of now we have defined just one layer of transformer block, but in practical situations the number of layers can be higher. Okay, and then we finally do another layer normalization. I think this is something that we have not done in this architecture, but it's just another layer normalization that we do, followed by the final iteration of multiplying it with this 4x28 matrix. So this is done. So this gives me my final set of logits. Okay, these final logits, and then I start training my model. Okay, and how does the training happen? So initially I define the loss to be none, and then basically I define my logits to be the inputs that are coming in this particular function, and targets, which is effectively the target tokens, right? So just to make you understand, so for GPT forward, the input will be this. Let's say this will be the input, and this will be the target. Okay, so it is going to consider each input and output pair, and then it is going to iteratively do the training and compute the losses. Okay, so this is where the training will happen, and this function will return logits and loss, so the updated logits and the corresponding loss. Okay, and again this function will also be used in inference. So in inference we will not have any targets, we will not be passing any target sequences, we will just be passing the input sequences, and so this entire chunk of code will be skipped, and basis the optimized weights the final logits will be given out, which will then be used to identify the next predicted token. So next comes the generate function. Now this is the function that will be used for inference. So the inputs to this function is first the input token sequence and the number of new tokens that we want the model to predict. So how it effectively works is that it iterates for the number of new tokens that it wants to predict, and in each iteration it first kind of truncates the input token sequence to a maximum size of L, which is 10 in our case, which is what we have trained our model on. So that is what it kind of takes as input. If the input sequence length is less than 10, then it obviously takes whatever is the input sequence that has been given. But yes, if it is more than 10, then it takes the last 10 input tokens, and then it calls the GPT forward function, which is something that we have already discussed, which then in turn iterates through the entire token embedding, position embeddings, then the transformer block, which takes care of the attention and the feed forward layer. And once the input logits are passed through the entire model architecture that we have designed, the final logits are given as outcome. Now additionally, because we are trying to generate over here and not train the model, so we are not going to pass any targets, so this entire chunk of code is kept, and the logits which are computed basis the updated weights that has been generated during the model training phase itself. So logits are now computed basis those updated weights, and final logits and losses returned. Okay, now the final logits is something that is equivalent to this particular matrix that you see over here. This is the final logits that we are taking into consideration, and for a given sequence of input tokens, it kind of picks up the last logit row. So for example, if we have passed in an input sequence token of length 10, which means like 10 tokens we have passed in, then it will pick up the last row. Okay, so this is what it is doing. It is picking up the last row and doing a softmax on that. So softmax basically means that it is then converting into probabilities such that all the probabilities sum up to 1, and then it gives me the token which has the maximum probability, and that particular token is concatenated to the end of the sequence, and then this new sequence again goes as input, and the iteration keeps on running till the number of new tokens that we want have been given out. So this is how the generate function works. So let me just quickly run this. Estimate loss. So this is something that we are going to use for calculating the training and validation loss at different intervals. Okay, so eval iters over here is the total number of iterations that we will be running, or total number of samples on which we will be running the loss estimation to calculate the training and the validation loss. So we kind of again extract random pair of input and target tokens, and using the GPT forward function. So this time we pass in both the input as well as the target tokens, and compute the losses, the training and the validation loss, and then we mean it for, or suppose, and then we basically average it for 200 iterations or 200 samples, and then we give the output. So this is how the estimate loss function works. So let's just run this. So here what we are doing is all the parameters that we have created, we are just collecting them together and passing it on to Adam Optimizer for the model to optimize these parameters. Okay, so Adam Optimizer is again one of the optimizing techniques that is used in model training. Learning rate. So learning rate again is one of the hyper parameters. So if you remember, we were discussing some of the hyper parameters that we skipped initially. So eval iters again is the one that we just discussed prior to this. That is the total number of sample size on which the training and validation loss will be calculated, and learning rate effectively controls that how much are the model weights updated in each iteration, in each training iteration. Okay, so let's collect all the parameters for optimizer. Let's see the total number of parameters. So total number of parameters is fairly less, 480 only, because what we have done till now is we have just coded up the architecture that we laid out on Google Sheets. Okay. Now what we are going to do is start the actual training. Okay. So we are starting a loop with a range of max iterations. So max iterations means the number of iterations that we want the training to happen. And over here is what we are going to do to calculate the training and validation loss. So every 100 training steps, we are going to calculate the training loss and the validation loss. So that is what this chunk of code is doing. Okay, so we pass on the input token sequences and the target token sequences. So we get them, and then we pass it on to GPT forward, which kind of takes care of the training. So as I already discussed, GPT forward then it basically calls in the other function, which kind of constitutes the entire model architecture. Okay, so let's run this. So we see after like 500 iterations, the losses have dropped slightly, but not significantly, because again, the model that we trained was fairly simple and small. Okay, so now let's try to see how this performs. So for that, we will be using a function called generate text. So over here, what we are doing is for a given prompt input, we are first truncating it to a maximum size of context window, which is 10 in our case, and then we are encoding it to convert it into token IDs. Then those token IDs we are converting to a torch tensor, and then calling up the generate function that we discussed. Okay, so this function, let's see how it goes. So let's say that our input is 101, 102. Okay, let's take that this is the input 101, 102. Okay, so you see that the response is 10, 60, 11, 480. So obviously this doesn't turn out to be good or helpful for us. And the reason for that is very simple, that this is a very small model, and the number of training steps is also significantly less. That is why it is not able to effectively understand all the interactions and nuances in the given context window. So what we will do now is we will scale up the model to see how it performs when we take a deeper architecture into consideration. Okay, so we'll make certain changes. So let's say that we take block size of 20, and so we are now increasing the block size, and we are also going to make certain changes on some of the other parameters. So let's increase the number of iterations to 5000, eval interval, learning rate, and eval iterations. So this we will keep same. Batch size also we will keep same. Now n embeddings. Okay, so let's scale it up to 128. So initially we had only 4 as the embedding length, so this is what we considered, 4 as each embedding length. Let's scale it up to 128. Number of heads, let's scale it up to 8. So we had just 2 heads, right, within each attention layer. So now let's have 8 heads, and number of layers to 4. So we had just 1 layer, which means that the attention plus feed forward combined, we just had 1 layer. So we are now going to have 4 such copies embedded in the model architecture. Okay, and dropout we will keep same, which is 0.2. Okay, so let's scale up the model now. Other part of the code remains same, no change as such. So another change that we have done is that we have increased the context window. So initially we just had 10 as the input sequence length, and similarly 10 as the output sequence length. So now we have doubled it up, so the sequence length has moved up to 20. So we are now going to pass in 20 sequences or 20 input tokens at once to the model for it to effectively learn the next token. Okay, let me also just change this to targets. I have interchangeably used the word targets and outputs, but targets effectively means that when we are training, so these are the targets on which the model is getting learned, and output is what happens during inference. Okay, so these are inputs and targets. Again, the context window has gone up. Now we have 20 token IDs in sequence that are coming in. Okay, I think remaining part of the code remains same. So another change that we will do is that we will also increase the size of feed forward weights. Okay, so if you remember, we were just scaling it up twice, right? So we had like 10 cross 4 matrix, and that we were multiplying it with a 4 cross 8 weight matrix. So we were scaling a 10 cross 4 matrix to 10 by 8, and then again kind of bringing it down to 10 cross 4. So 2 times, right, is what we were expanding and then collapsing. Let's do it 4 times, just because, so that we can have more weights and better training. I think other part remains same. Okay, I think all the other parts remain as it is. So let's quickly see how many parameters. So see, the number of parameters have gone up considerably. So now we have close to 73, right? So this is like 7.3 lakhs. Okay, so now let's run the training. Okay, so our training has started, and now as you can see that the number of parameters have gone up, the training time also goes up. but we see that the losses have started showing reduction. So we'll wait for some time, and once the training gets completed is when we will see how it performs. Okay, so now our training has completed, and we can see that the losses have gone down considerably, and on the validation set we almost see that the losses are kind of reaching the optimal point. Okay, so so now because the losses have gone down considerably after 5,000 iterations, let's just test it out that how the model performs now in terms of output. So let's test the same example. So for 101, 102, the previous architecture that we had did not perform good. So let's see how this, I think, a bigger model turns out to be. Okay, so the response that I have got is 103, 104, 105. So as you can see that the model has been able to learn the relationship between different tokens very effectively, and it is doing a pretty effective job in terms of predicting the next token in a given sequence. Let's also try a few other examples. So let's say 521, and let's say 522. So 521, let's see what the model predicts. 523, 524, 25, so on and so forth. So it is doing a pretty decent job. Let's see if we reduce the context length. So this is where it kind of struggles little bit. So after 1, it predicts 392, 393. So it goes into the 300 series instead of directly predicting 2, 3. But maybe if we increase the context window and let's say we give it a longer context up till 8, and then let's see how the prediction works. Okay, so this still struggles a little bit. Let's try increasing this further to see if there is an improvement. So yes, so you can see that after 9, 10, 11, 12, 13, 14, so on and so forth, the predictions seems slightly better off. So that's it. I think with this we conclude the second objective, which is code and train a simple transformer architecture on a small data set using Google Colab. Now what I have also done is I have created a parallel Google Colab notebook in which I think the code is more modular, and we have kind of used class and objects to make the code a bit more modular, and the models can also be saved and used for later use cases. So I'll be sharing the link of both the Google Colab notebooks. So feel free to go through it and try it on your own and see if it makes sense. Just another thing that I wanted to mention out. So over here you see that whenever we are let's take example of feedforward network. So whenever using PyTorch we initialize weight matrix, so it not only initializes the weight matrix that we have discussed on the GPT architecture on Google Sheets. So if I take example for feedforward network, we are just assuming that this is the matrix that gets initialized. But what PyTorch does and what happens in actual model development or training is that there is also a bias matrix that gets created, and how the matrix multiplication then happens is that, so first row multiplied by first column, and then the bias term is added. So a bias matrix whose dimension will be 8 in this case is also that is taken into consideration, and that also is a learnable parameter. So that's mostly it. I think this concludes the session, and the broader idea and goal behind recording this video was to give you a very intuitive understanding of how ChatGPT architecture works and how we can code a very simple architecture to get a feel of how transformers are actually created and implemented. Nevertheless, I think when we are training production grade systems, a lot of other factors also come into account, and obviously the architecture is much more denser, and the computation power and resource required is very high as compared to what we have done till now. But fundamentally, at the heart of it, this is what happens behind a powerful LLM. So that's it from my end. I think you probably must have enjoyed watching the video. If you are still watching it, that makes me assume that you have kind of found it interesting till now. And so yeah, that's it. Thank you guys. Thank you for joining in.